Recording has started.
Is it correct that we don't hear anything, or?
You guys hear me now?
Yes.
Oh, cool. Just so you know, I hear my voice back, so maybe you mute your microphone unless you're asking questions.
Yes, let me do that. There is a mute button here. Okay, it will be muted now.
All right, cool. Hello, everyone, and thank you for coming. And many thanks to Carlos and King for hosting us, and to Mikel and to Ray for rallying the Barcelona and Amsterdam meetups. My name is Cal, and I'm an engineering lead at MongoDB, and I run the part of distributed systems that deals with horizontal scale-out. I have some script here, so I'll read it from time to time so I don't forget what to say. I'm based in Barcelona, actually in the WeWork that's right around the corner. But I've been at MongoDB for about 6 years, and I started in New York. And I've been in Barcelona for about 3 months now. The goal of my talk tonight is to not to give an exhaustive overview of everything MongoDB or really deep level. It's just to give kind of a high-level overview of the engineering and the source code behind it and the different subsystems. And then my hope is that at the end of the talk, when we're done with the slides, we can, based on interest, we can go into some more details and so on. My talk is kind of going to be structured like this. My assumption is that not everybody in the world knows what's MongoDB, so I'm going to spend a few minutes to just introduce it and what it is about, and what differentiates it from other databases. After that, I'm going to present some interesting facts about the engineering and the source code behind it in order to set frame for the rest of the talk. Because this is a C++ meetup after all, I'm gonna start from the bottom with the basic C++ building blocks and components and platformy things that we built. And finally, because this is my strongest point, I'm gonna talk about MongoDB sharding. And maybe in a few minutes, my colleagues from New York are gonna join in, just in case you guys ask me some really difficult C++ question that I might not be able to answer. So I'll have them answer it. If you have any questions during the talk, feel free to interrupt me. I'll try to answer them. But if it becomes more of a discussion, we'll just leave them for the end of the talk. Cool. So what is MongoDB? Our marketing team defines it as a universal database for scalable and modern applications. What does that mean? How many people from here have heard of MongoDB? Oh, so pretty much everyone knows about it. And heard the name. At least they have heard something about it. Yes. Well, that was going to be my second question. How many people have used it for work-related or for fun? About a quarter, I guess. A little less than half, maybe a third. Okay, that's a pretty good number. So MongoDB uses the document data model, and I'm going to explain what this is by contrasting it with the relational data model. Supports flexible schema, which is another thing that differentiates it from traditional relational databases, where it's very difficult. You have to run like an overnight job to add a column to your table and so on. And also, as of the latest release, supports ACID transactions, ACID meaning atomic, consistent, isolated, and durable. Cool. So what is the document data model? In order to explain it, I will contrast it with the SQL relational data model. In the relational data model, we have tables, and the data for we have some application level concepts. Let's say we have a person and their property. People have houses, people have cars, sometimes one, sometimes many, and in a relational data model, everything is normalized. We have one table which has all the people, we have one table which has all the houses, and we have one table which has all the cars, and then there's some complex joins run between them in order to find which person has what houses and cars, or which car belongs to which person, and so on. Usually, developers don't want to program by running queries against the database, so usually there is some form of object relational mapping that gets put in the relational database that makes the concepts in the database look like the objects in the application. So in our little example, we're going to have a class person, and the person is going to have a get houses and set houses methods and get cars and set cars method. And the ORM behind it does the mumbo jumbo with running transactions, running joins, and so on to present what's in the database or to update the database based on what the application does. And usually these are kind of joins based on foreign keys where the house ID of the person is linked with the houses table, and then there is more detail in the houses table and so on. And in my example, the relational model is pretty small. There's 3 tables, but in real world applications, those data models become kind of pretty crazy. This is one example of a data model. There are like about 12 to 15 tables here. And believe it or not, there's data models that look like this. So it is pretty crazy. The document data model, in contrast, tries to put the data together. All the data that's for a specific application domain's object tries to put it together and present it in a way that most naturally fits the application, which is making it look exactly like the application's object. There are no more joins. There's no more need for normalization. The database takes care of how actually the data is stored, but it presents it as objects. There's pure object mapping with what the application code looks like. And the data model, the document data model is very powerful to program against, but it also, because it's not relational, there's no need for joins and so on. We can take some shortcuts in order to improve performance or in order to improve distributed synchronization as the data grows and gets bigger than what a single node can sustain. Carlos, did you look at me? Okay.
Trying to start
Okay. MongoDB as a server is typically deployed in 2 different configurations. The first configuration is called the replica set, and its only purpose is to provide high availability, and in certain cases to also spread the read load, so you can read from the replicas. This configuration has typically people deploy it with 3 nodes in 3 different data centers. So if one data center burns or catches fire, then the other 2 can take the load. And the 3 nodes, and there's one node which is primary. This is where all the writes go, and writes get replicated by the secondaries. And the nodes constantly monitor each other, so that if one node dies, let's say the primary dies, the nodes are going to run a consensus algorithm, which is based on Raft is the algorithm. They elect a new primary. So one of the secondaries will get promoted to a primary transparently. And because the driver is also aware of what the replica set looks like, this failover happens transparently to the application. So there is no, from the point of view of the application, you don't get like error 500 from the server or something like that. You just maybe blocks for a little bit and then it continues. There's a small latency increase. So this was the first deployment configuration. The second deployment configuration is called sharded cluster, and it's a little bit more complicated. The way it works is by taking one of these replica sets that I described before, putting a router in front of them to bind them together, and this router speaks the database protocol basically. and it pretends to the driver that it is the database, but internally it routes queries and writes to wherever they need to go. And on top of this, there is an infrastructure, and I'll talk about this a little bit later. There's infrastructure in the sharded cluster, which moves data around in order to make sure that no node becomes too big or that there are no hotspots and so on. Basically, even distribution. Architecturally, in the MongoDB, if you take one server process and kind of open it, peel it open, architecturally there are there are about 10 different subsystems that closely correspond to how also the teams at MongoDB, the engineering teams at MongoDB are organized. And I'm going to walk you through how one request in MongoDB goes through these layers. A request comes on the network accepts it, parses it, and says, oh, this is a find command, let's say. Then it goes through the security system, which where it checks, oh, does this user have the permission to run a query on that on that collection? Collection, remember, is the MongoDB equivalent of tables. I should have clarified that. Then once security is processed, the query goes to the query parser and planner, which builds a plan about what indexes to use and what data to fetch and how to execute the query in general. Then it goes to the query execution engine, and the query execution engine it starts executing the request, but it also uses the replication subsystem in order to perform checks. Oh, should I, for example, if the operation is a read, and that read needs to read from the primary node only, that's the replication system. Are you still a primary node? Am I allowed to read that data, or otherwise it just fails? And similar, if it's a write, it checks, is this the primary node? Am I allowed to write this information? And if not, it fails. And once all these checks have passed, it starts issuing requests to the storage engine, which is to actually fetch the bytes from disk and return them in user visible application information. And at the bottom, I've drawn it as the thing that underlies everything, but actually it should be everywhere in between, is what we call our platforms code. And the platforms code are basic building blocks for concurrency, for thread pooling, things that abstract the hardware. For example, we have data structures that represent integers, but they serialize depending on whether the system is big endian or little endian. They know how to serialize that data, but for the point of view of the code, they present it just as an integer that should be used. I want to put one slide just to kind of give a scale of what the company looks like. The company was founded in 2009, so MongoDB actually has existed since about 2010. I think that was release 1.0. 2009 probably was 0 point something. And currently it's 1,600 employees. Of these employees, there are 300 engineers, split roughly around 2 large organizations. One of the organizations that I belong to is called Server and Drivers, and it has about 200 engineers in 5 different countries. Our biggest office is in New York, but we have offices in Ireland, Australia, Germany, and now in Spain. Also, one interesting fact to mention is that 4 of the members of the server team are on the C++ meeting committee, which gives us benefit in influencing some of the decisions and how the APIs are built, but also causes some very heated, opinionated discussions during code reviews about how things should be implemented. So it's a double-edged sword. And so this is the server organization. It's mostly C++ developers. And the other big organization is called Cloud, they build everything that's outside the server. We have a MongoDB hosted solution where you just go to some website, click a bunch of buttons, and it gives you back an IP address. And you just connect your application to that IP address, and the cloud infrastructure behind it makes sure that an instance is taken from AWS, that it's formatted, that MongoDB is installed on it, and it's stitched together into a cluster. It gives you back metrics and stuff like that. There's also integration with alarms, so if your MongoDB load reaches some threshold, you get paged at 3 a.m. at night and stuff like that. The MongoDB server code base is open source and it's hosted on GitHub. And last week I ran LOC and it consisted of 860,000 lines of C++ 11 code. But if you include, so we have a C++ unit test framework that we test like small components that we write. If you include those, is 1.33 million lines of code. In addition, we have a JavaScript framework, which we use to test the server directly. So the server is running, we issue some queries around it. That framework allows us to kill nodes or to crash this, to kill -9, like to hard crash it, make sure that it recovers properly. Sometimes it allows us to mask, for example, dropping packets. What happens if the packets are dropped or if they get reordered and stuff like that. So we write this kind of tests sometimes with JavaScript. And all these, we have a continuous integration environment, which after every commit to GitHub, it runs the whole test suite. So we run our tests pretty frequently. Costs us a lot of money, and we're trying to figure out a better way so that we don't miss bugs, but also we don't spend so much money on running up, because there's a lot of commits. We have a lot of people now, and they commit a lot. Cool. The MongoDB server and the C++ unit tests are built using sconce. How many people here have heard of sconce before that? Oh, okay, so 2 people have heard. I'm pretty sure we might be the only user of sconce, but I'm not sure. And I don't know why we chose it, but it's a Python-based build system, which basically makes your build kind of look like you're writing a Python program. I have no opinion about it, but it's been like there for 6 years and it's working pretty fine. We build and test the server on more than 12 different platforms, which start from the most popular, such as Linux, all the Linuxes like Ubuntu, RHEL, 6.7.2, and so on, and Windows, to some pretty exotic ones such as ARM, PowerPC, and the IBM 360 mainframes, which are big endian or little endian. I forgot which one it is. But we build for both endianness, and believe it or not, we also build it with using the iOS Apple Watch SDK. I'm not sure why, but we build on everything. In addition, the server uses some of the more popular C++ open source libraries, such as Boost. We're currently at 1.70. Asio, this is what we use for our networking code. We've linked Moz.js, which is what we use to execute Java. Like the server has the ability to execute JavaScript, something kind of like stored procedures, and we use Moz.js for that. And also, we recently vendorized something called Upsale, which is the Google utility library, and we use it for to replace the unordered map. So it has a better implementation of the unordered map that gives us better performance, and we use unordered hash maps a lot in the server. So this gave us some performance boost. Cool. Here, in this slide, I'm going to discuss some of the reasons why we use C++. Being a database server, if you exclude correctness, that we shouldn't lose data and stuff like that, the most important requirement that MongoDB has is that it needs to have a predictable latency and throughput. There cannot be random blips of high latency or throughput dropping to zero. And obviously, garbage collected languages are not good for this. So Java and stuff like that are not, I wouldn't be good for it. And with C++, we have the benefits of being able to model everything using an object model, but also we have direct access to memory allocations and deallocations. Also, the C++ compilers are very, very mature. There's a lot of optimizations that we take benefit of, and that makes our database better. We also use the support for exceptions. As one interesting side note, because we can't control the memory allocations that STL does or that the STL containers do internally. I mean, you can, but it's kind of difficult. You have to put allocator and stuff like that. And also, because we link third-party libraries, we can control how they allocate memory. We swapped the default CRT allocator for something called tcmalloc. And tcmalloc is an allocator which uses per processor cache of 3 blocks, so that for tiny allocations such as stud string and the little building blocks of map and unordered hash map and so on, those allocations are practically free because they just go to the local processor's cache. There's no contention on a central mutex. And with the default CRT allocator, there's a lot of contention on the central mutex. We use the standard C++ features. We don't use anything crazy. Stud vector, set map. We use smart pointers, boost optional, unique pointer, and shared pointer. The use of shared pointer, interestingly, is a bit contentious because being a database server, it turns out that sometimes we have shared pointers to to objects that consume a lot of memory. Imagine a plan cache, for example, that's 100 megabytes of memory. And when we use shared pointers, we don't know who has references and why are there, for example, 1,000 plan caches available and the server runs out of memory. So in certain cases, we actually prefer using intrusive pointers so we can control the who takes a reference of an object, and we can keep some kind of registry. That way, a customer whose server is reached almost the limit to be killed by the allocator can log into the server and run something similar to top, and it's tell it, oh, you have a plan cache that's 500 megabytes that you have this one long-running query has been holding it for an hour, for example. So they can go and kill that query. From the synchronization primitives, we use stud mutex condition variable, nothing crazy there. An interesting fact is that we wrote our own implementation of stud mutex and of the futures. And I'm going to talk about this a little bit about why we did that. And finally, we use stud thread, but we don't usually do it directly. We have an abstraction called thread pool, which controls how many threads are created and tries to retire threads so we don't keep too many threads around. Otherwise, if we just use stud thread, it was kind of a chaos. You end up with 200 threads and you don't know who created them. So now we use pools instead. We're currently using C++ 17, and it took us about 5 years to get there from C++ 98. I have a question for you. Raise your hand. How many people at one point or another thought that there are no bugs in the C++ container, in the C++ compiler? Well, but how many people assumed or took it for granted that the C++ compiler cannot have bugs? It's perfect. Yes. And how many people actually spent weeks trying to figure out like some subtle bug and it ended up being a compiler bug? Yep. So that's why we were very afraid of adopting the new the new compiler. So the way we did it is we in development in the development release we use the new version, but we still keep the released software at the old version, and kind of over the years eventually reached to C++17, and so far from what I understand it's been running fine. Now that it's been more than a year since we're using C++17, these are some of the most used features that are widespread throughout the code. If const expr, if initialization, class template argument deduction. The guaranteed copy elision actually was very useful because we could make like some large objects that are being returned by functions to make sure that actually we could remove the copy constructor and just leave the move constructor and make sure that they're not actually copied. So we found a bunch of places like this where we were copying a lot of memory. So we gained some throughput from that. Structured bindings, inline variables, and no discard. With this, we discovered a lot of places where we weren't checking, for example, for proper return values, and we were missing error conditions and so on. In our code base, we have made it a point to avoid using global variables. So the way the server works is, I mean, we still haven't gotten 100% there. There's still some global variables. But the idea is that in the main of the server, we instantiate a single service context object of which everything that's related to the server hangs off of it. And that service context is passed through to every thread and every subsystem that needs to use it, and it picks from there whatever it needs to access instead of reaching into global variables. And why we did this is because now within a single, let's say we're writing a unit test, within a single unit test, I can spawn 2 or 3 servers in the same process space. There are 3 servers. I can mock their network, and then I can write tests that interleave different messages or different thread interleaving. So we do test a lot of concurrency race conditions like that. It's very useful rather than testing the server with some stress testing from randomized stress testing from outside. We implemented a cool framework called decorations in order to dynamically extend the service context with child services. So that way, if you have 5 different services, well, we have more than that. There's probably 20 or 30 things that hang off of the service context. We don't have to forward declare them, put a pointer in the service context class. Instead, the decoration framework works something like this. There's a class called decorable, and service context is defined as decorable. And then within the CPP of every component that we do it, that needs to have some global component. We declare a decoration, and the way this works is that there is one global variable which contains a vector basically of all the decorations that are declared, so that whenever a new object is instantiated, it just uses that as a template for how much memory to allocate, and every decoration knows its address in that array. So this ensures encapsulation as well. So for example, the logical sessions cache doesn't need to be seen by the storage engine or something like that. So there's some form of encapsulation. I wasn't sure whether to include the slide on startup and shutdown, but because it's the seemingly simple, trivial part of the application can cause so much grief, I decided to include it. Raise your hand. How many people are familiar with the static order initialization fiasco? So static order initialization fiasco is when global objects try to access, one global object tries to access another global object before it has been initialized. This is before the main method runs. And we chased the numerous bugs where one class runs and tries to call something into another class and put some state into another class, then the other class gets initialized, wipes out that state, and now it's lost forever, and there's subtle bugs that you can't figure out why they're happening. And they only happen on Windows, or they only happen if you rename a file because it starts sorting before that, and so on. So we decided so we implemented our own initialization framework where first all the objects are initialized, and you're not allowed to access anything else in the constructor of these objects. And then there is an initialization function an initialization macros where you put, I want to initialize my logical sessions cache, and it depends on that other component. So it basically builds a dependency initialization tree that gets run, checked for cycles and stuff like that. And the same thing happens on shutdown. We have a shutdown functions that get executed first, and then the static destruction happens. And in order to enforce that these things are obeyed, we started running everything under ASAN and UBSAN, which is address sanitizer and undefined behavior sanitizer. So we cut a lot of bugs through that. So we have adopted two means for handling errors on the server. One is called the class called status. So if you must return an error code, you cannot return int, and that int 1 means something, 2 means something else. You have to return an object of the type status, and the status is either okay or it contains an error code, descriptive message, and possibly extensible error info. And same with exceptions. All the exceptions have to derive from a single class, which is called DB exception. And there is one-to-one conversion between the two. Status can be converted to exception. Exception can be converted into status. And what's nice about it that if we have the main networking code which accepts a request, a command, and it's doing something, goes into some stack, and then somebody throws an exception, and that exception bubbles all the way up to the networking stack. The networking stack can just use the code, the message, and the extra info to construct an appropriate response to the user versus returning something like std exception and stuff like that. So we can put a lot more descriptive information, and there's like 6 places where we can put it.
Do you stack the codes as you're moving on, or you just keep the last code in the back on the bottom part of the stack?
Can you start over? I missed the beginning.
Do you stack the codes, or do you use a single code when you're informing the network that something happened right below?
So the question, as I understand it, if I enter, let's say a query is executing, and somewhere down there I get a code, I don't know, out of memory or something like this, do we return it as out of memory, or do we translate it to something? Okay, it's a very good question. We do not stack the codes. There's no stack of codes like in Java where you can wrap one exception into another. We translate them. So if I don't want to return no more memory to the user, I can intercept it somewhere in the middle and say your query failed because you're using too many predicates or something like that. But there's no stacking. Yeah, good question. So I mentioned earlier that we implemented our own custom features. So why? I'm going to talk about why did we do this. Turns out that in a database server, when a customer submits a request for some query, usually they're not interested in waiting forever. Usually they specify some kind of a deadline. For example, I want that query to return within 5 seconds, and just give me whatever results it fetched, and don't worry about the rest. I don't want it to sit for 1 hour because maybe my application now it's stuck. And also users want to be able to see what queries are stuck in what, and to kill them and basically interrupt them into whatever they're doing. And the C++ standard features don't offer a good way to do that. They basically have a wait for, where you can pass a deadline, but this means that you have to have a loop which sleeps and checks has it been interrupted, which is not very efficient. So instead, we implemented our own feature, which kind of looks like the one in the standard, but it accepts an interruptible object, which can be called if you want that thread to stop waiting, and then that thread will throw interrupted exception or deadline exceeded exception and so on. Another thing that the features from the standard don't offer is control over which threads execute the continuations of the features. So it means that we had issue, for example, where there is one asynchronous networking thread which is signaling a future, and then in the continuation of that future we write to disk, which is a blocking operation. So now we've blocked the single epoll thread of the asynchronous networking. With the ability to control which threads execute, now actually we can put a different executor or different thread pool to execute the continuation, so that the main thread can continue. Also, by having our own features and the interruptible class, we know at the runtime who's waiting on what, so that if a customer's server is blocked, they can run something similar to top, and it's going to tell them, oh, this thread is waiting on this query, is waiting on data from this node or something like that, versus every time something gets stuck, we have to ask them to run GDB, and then we have to look at the stack dump and so on. And also it gives us richer integration with error types and exceptions that I described. We also implemented our own custom mutexes for the same reason, to have runtime diagnosability and deadlock detection. And deadlock detection is particularly interesting because when you make a mutex, so basically this is what the mutex creation code looks like. And I believe you can also add a number which specifies what level that mutex is supposed to be running at, so that this enforces order of mutex acquisition. So you don't have, if you have thread from a lower order acquiring a lock, if you have a thread of a higher order acquiring a lock before a thread from a lower order, this means that you've inverted the order. So now that there's a deadlock, and that crashes at runtime. And also we have some static analysis tools that can see that as well. So now we're able to catch, we're able to preventatively catch deadlocks. So your question is whether futures and the custom mutexes can be used by themselves without the engine, right? There's nothing in them that depends on all the other code in the engine, other than maybe classes like this, which are only interfaces. So they're not meant. We're not publishing them as a separate library that you can download and you can use. But with very little work, it can be peeled off and be made by itself. One other thing I forgot to mention about the features is one of our engineers did a perf testing of the features from the standard, from the C++ 17 standard, and our implementation of features, and he discovered that they were actually much slower. The ones in the standard are much slower than the ones that we implemented, and specifically in the case where you create a ready feature, so basically a feature that already has a result, is practically free with our implementation, but in the one from the standard, there's memory allocation or something like that. So it's much more expensive. Yeah, and with the mutexes, we are also able to discover what are the hot mutexes without having to attach GDB or perf. We can implement our own top tool so that so we can keep statistics basically on when it happens. Cool. So this is all I have regarding the basic building blocks and about C++ and stuff like that. The rest of my presentation is about MongoDB sharding and some of the distributed systems algorithms that we're using. I wanted to see if there are any questions that I can address before I move, because they're kind of too different. Yes?
Yeah, you might have mentioned it, but is the futures code open source or no?
This is also what, so all of the server is open sourced and the futures code including, yes. But it's not, you can't just take it. It depends on some other types and infrastructure from the server, but it's not, yes.
But with your future implementation, you can decide which threads that would serve as a configuration. Do you have a default behavior for that, or you are obliged to configure it like in C#?
So your question is, what is the default behavior of a future? Who executes the continuation?
Yeah.
And by default, if you don't specify, we call them executors. If you don't specify an executor, it will execute on the same thread that signals that sets the future. Okay. Yeah. Yep.
You mentioned that unit tests are run after each comment, and it costs a lot for you guys. What is the reason that it costs a lot?
So we have three types of testing. We have unit tests, which are basically you just take one class and test it in isolation. Those are cheap to run. Those are very. We have a lot of those, and those are very cheap to run. In terms of time and in terms of computing resources, I believe all these tests, if you take one AWS instance that has 16 CPUs, let's say, and you run it with 16 different threads, those run probably for 2-3 minutes there, and they're all executed. Let me just finish. The second level of testing is what I described with the JavaScript testing, where actually we spawn an entire cluster. So you have to, let's say for sharding, you have to spawn at least 3 nodes for the replica set, the router, the whole infrastructure around it. So this is expensive. We have hundreds of these tests. So those tests take a lot of time to run. So we have, let's say, recently we did the math of how much time they run, but let's say we have about 450 sharded tests. To run these tests sequentially, something on the order of 6 hours or something like that, after each commit, on 12 different distributions. So this means you have to, but you can't possibly run them for 6 hours, because if testing takes too long and you make it difficult for developers, they tend to check in the code regardless optimistically, and then chaos ensues usually. So we parallelize them. So now you have to use 6 machines, so it runs in 1 hour. And so our AWS bill is kind of astronomical because of this. So in that sense, it's expensive. Yeah.
Why is it called
So internally we don't use pull requests. We do git push. So the question is why we run all the tests after every commit. It's not exactly after every commit. The way it works is that it runs occasionally the the continuous integration framework, sees what commits. So let's say that there are 10 commits, and then it will run the latest one, and it will check if everything is green. It's actually not going to run the remaining 10 before that, because it assumes everything's fine. But if you have like one little red somewhere, and our tests are kind of flaky, so they fail for either a bad written test, or AWS was doing maintenance, so something took 10 minutes and stuff like that. So then it's going to backtrack and run each one of them to bisect and find if there's a bug. So from that point of view, it's we do code reviews internally. We used Google Rietveld for code reviews. The question was whether we use code reviews, and we don't push directly to master. We use a code review tool which is called Rietveld or something like that. It's a Google code review tool. It looks like a 90s website. It's very bad, but it's I'm not sure why we're using it. I think it integrates very well with GitHub maybe or something like that. You had a question?
It's more of a business question, technical question. How come you guys are still on AWS given A, the expense, B, their use of your API in a manner that is.
So the question is, why are we using AWS given that they're expensive? You have to pay for the instances that you're using, and given that they implemented DocumentDB, which has the. I think I'm not sure, to be honest. But I think between AWS, Azure, and Google Cloud Services, they're all the AWS is the cheapest, and they have the spot instances where you pay very little money for your node, but if somebody who pays more than you comes, they kick you out, and they shut down the node from underneath of you, and I wanted to see if I forgot about the Amsterdam group. I wanted to see if there's any questions from there. Do you guys have any questions?
Do we? I think. Oh yeah, one question.
A question
Yes.
regarding this pointer. So you mentioned performance gain, but does it really come from the fact that it's together with the counter and the data? Because we can argue that you can simply use make share.
I did not
get that question. Ray, can you repeat it?
Okay, let me see if I can. So the question was about the performance improvement over the boost shared pointer, right?
A boost intrusive
intrusive pointer.
Compared to shared pointer,
if it was related to sharing, storing both data and counter.
Related to the way it stores the data, or is it related to the fact that the counters are atomic in the shared?
Okay, so is it related to whether the counters are? Can you maybe come? I cannot rephrase. It's easier. I can have it in my mind for a few seconds and then.
Hey, yeah, the question is regarding the usage pattern of shared pointers. So as I understood, you switch to boost intrusive pointer, and then you get that performance gain. So I wonder, does it come from the fact that it stores the data altogether, or from the fact that the counters you provide are not atomic?
Okay, so the way I understand the question is why we get performance gain from using intrusive pointer. And I apologize if I said that, but I don't think we get any perf gain from using intrusive pointer. We actually the reason why I mentioned we're using it is because we have a control of who can keep track of the people that are referencing some object with a large that takes large amount of memory. But in terms of perf gain, I don't think we're getting any perf gain.
Cal?
Thanks. Can you hear me?
Do you guys hear me?
Yes, oh sorry, it's automatically muted, but it's clear, thanks.
Oh yes, after you guys ask a question, can you mute yourself? Yeah. Cool. Any other questions from Amsterdam?
Yes, one more.
And then muted.
The question is about the features in standard library. I mean, can you elaborate why are they perform worse? Then I mean you have 4 how is it members of committee. You know, just make
So
them
the
better.
question is why the features from the standard library perform worse than our features. And I noticed that my colleague Matthias joined, so I'm going to defer that question to him. Matthias, are you there?
Yeah, can you hear me?
Yes. Speak a little bit louder, or maybe closer to the mic.
Okay. Is that any better?
Yes, much better.
So just to add to the prior, the intrusive pointer, one thing that it does save is because it doesn't support weak pointers, it avoids an atomic decrement on deletion. So we are still using atomic ref counts, but it is you only need to do 1 rather than 2 for when you destroy the object because it doesn't support weak pointers. So that's one thing. Also, we are able to do some useful things with buffers where we allocate a buffer that includes the shared pointer. And that's trickier to do with the stud library. As for futures, so one thing to know about standard libraries is that they care about ABI, which is good if you care about shared objects and the ability to replace them, or have a really old library communicate with a really new program, or vice versa. But unfortunately, it means that they basically can't change anything. In terms, they can't change internal implementation details. It's a bit of a problem. And so most of the implementers know that the implementations of shared pointer are not, or of futures are not great, but it is, unfortunately, they're not able to change. In fact, if you ask most of the implementers, they have a long list of things that they hate, would not recommend anyone use, but are unable to fix. It's unfortunate. But as for a specific reason, at least the libstd C++ version uses call once for some of its implementation. Specifically, when you complete a promise, it goes through call once. And that is horrifically unoptimized and always traps into kernel. And that got hit with an additional penalty with the Spectre mitigations. So it is really bad now. It wasn't good before, but now it's really bad.
Thanks, Matthias.
Cool. Does it answer your question?
Yeah, unexpected.
Yeah. Great, thanks.
You had a question?
Yeah, why saying about future robotics, but why the only implementation variant if you have the STD version in C++ 17, or you can use Upsailors or Boost?
Okay, can you restate?
A specific implementation of a variant if you have different options. You have the Boost, the stud version in C++ 17, and also in Upsail, I think we have the only.
So your question is about what usage of which implementation of variant do?
Specific version of variant.
So the question is which one do we use?
No, why you have a specific version you told before.
Oh, not variant, boost option, boost optional.
Oh, okay.
Yes. We don't have our own implementation of variant. We use the one from Boost, I believe, for purposes that something's not working with the one from the standard.
We're actually using the mpark version. And it just has a better implementation than the stud one. The stud one implementation is, specifically visit, is pretty bad.
Yes.
So I have a question about sharing the code around that. You get a lot of outside that are meaningful, or rather your team that works specifically for MongoDB does the work. And yeah, what is the quality of the external contribution? How do you think about that?
Cool. So the question is around the open source of the database. Why is it open source? What is our benefit from that? and what kind of contributions do we get from the community. And so to the first one, why is it open source? It's for multiple reasons. It helps with just attracting developers. So for example, when research institutions see that the server is open source, they now can use MongoDB for research. They when we hire people from universities like that, they already have some. So it definitely helps with recruiting and spreading the word. So that's one of the things. In terms of the kind of the contributions that we get, usually the contributions are for very specific things. They're fixing something, some small annoyance, or we have, for example, something called the aggregation framework, which is similar to doing a join, I guess. And it's similar to a pipeline of in the Linux shell, where you take the output from one command, pipe it to another, and so on. So the people, for example, implement their own operators for the aggregation framework. This is the kind of contributions we usually get, or they add support to build on some fancy exotic platform. And I'm not sure, it might be that the ARM build came from a pull request, but I'm not sure. And so that was the other question. In terms of quality, we don't get that many. We usually get, I don't know, a couple a month or something like this, sometimes less than that. And quality, sometimes it's good, sometimes it's really bad, and there's somebody who rewrote the whole server. There's 200 files changed, so obviously don't accept those. Does that answer your question? Cool. Yep. So the question is, if MongoDB is open source, how do we make money? And so MongoDB is, and I can't say too much here, so I don't say something wrong and then spread the word. But we are licensed. Even though we are open source, we are licensed under something called server-side public license or something like that, which is similar to GPL, with the additional requirement that if you take the MongoDB source code and you use it for you expose it as a service. Let's say you build your own MongoDB in the cloud service. You have to open source your software as well. So even if you host MongoDB for this purpose, you have to open source your software as well. And a lot of companies, for example, prevents us from from Amazon just taking MongoDB and putting it and calling it DocumentDB. This is one of the backstops. to say it shortly, yes. For example, we have in China, we have Alibaba who hosts MongoDB and expose it, but from what I understand, we can't really enforce that in China. So there is a MongoDB service in China. Yes.
Wait, so they actually took the whole thing completely and are just exposing that as Alibaba's own version of this? So
I can't really say that, but I know that there is a MongoDB service on the Alibaba cloud for a fact. That's all that I can say. Yes. And from time to time, we do get requests. They definitely know. They are very good, smart developers. They know our source code almost as good as we do. So that kind of adds up a little bit, but I can't say anything. Yes. Yeah. Did it answer? Oh, yeah. So the rest of the question is, how do we make money? I don't know exactly the specifics, but because even though it's open source, you still have to open source your code. So there is no there's no motivation for customers to just take it and sell it themselves. I think it used to be that majority of our income comes from enterprise. Oh, I forgot to mention, even though we're open source, we have enterprise repo, which contains enterprise features like for example, integration with LDAP, with Microsoft directory services, like things that the very enterprising customers would use. So those are paid customers. Those are not part of the repo. And it turns out like big banks or big financial institutions, they actually need these features, and they also. But I don't think that's also what makes the majority of the money. It's consulting and just ability to penetrate new markets and replace Oracle and some legacy applications. So yeah. So this used to be the majority of what makes money. Now it's been I believe 2.5 or 3 years since we have Atlas, which is the MongoDB hosted solution. Which you just go click a bunch of buttons and you get an IP address. That thing has surpassed, I believe, revenue, and it's kind of going uphill. How much the usage and revenue has gone from Atlas. So the hosted, the managed solution has been a big hit. Yeah.
I have a small question, if it's possible. We didn't discuss it up front. Does it make sense to have maybe a short break before we continue with the second part, or is this not? I don't know if you had a different schedule in mind.
I am pretty flexible, but I believe we already use. Can you mute the mic? Can you mute the mic, Ray?
Yes. It should be unmuted.
It's better if you now and then extra time.
So the rest of my presentation is I have about 15 more minutes probably for sharding. If you guys feel tired, if you think it might be more appropriate to do it as a separate talk where I can include more detail, I can do that as well. So we can call.
It was just a suggestion. I thought maybe if you're halfway, then we can just do a short break, but I'm fine with both.
Should we? I think we should either finish it or okay.
Let's just go ahead then.
Cool. Yep. Yeah, the rest of my presentation, because we didn't have too much time, we wouldn't have too much time left, is about, I want to give some details about MongoDB sharding and kind of just to demonstrate one of the distributed systems algorithms that we use, because it's pretty cool. And then if there is interest, we can organize another talk where I can provide more details about that. So I'll go quickly through this. I know you guys are tired, probably hungry, and I want to have a beer. So we can. So what is the purpose of MongoDB sharding? It's a system to horizontally scale out data when the resources of a single node, like the CPU, the memory, and the disk of a single node, are no longer sufficient for whatever workload is being run. And vertical scale out is no longer impossible. Vertical scale out means when you buy bigger and bigger hardware. And the sharding system presents a unified view of the database server by putting a router in front of a set of nodes and routing requests through it. And one of the most attractive features of sharding is that it periodically rebalances data without incurring downtime to the application, without stalling it, and so on. So this is kind of how it looks like. Let's say we have 3 shards, shard 1, shard 2, and shard 3, and we have, let's say that our data is partitioned by first name. That's not very useful partitioning, but let's assume that's how it is partitioned. And on shard 1 is from -infinity to the name Igor. I have the round bracket because it doesn't include Igor. Igor goes in shard 2. Shard 2 is from Igor to Rachel. Rachel to infinity is shard 3. And based on where what name is sought by the router, it routes to the appropriate shard. That's pretty straightforward. In the subsequent slides, I'm going to introduce you through the architecture of sharding and go through the lifetime of one request, and that's pretty much what I have for now. So bear with me. So sharding is typically deployed in this configuration. There are three types of nodes. We have the shards in the bottom, which I already described. Each one of these is 3 nodes for high availability, a primary with 2 secondaries, and this is what contains the data. We have the router, which is what the application and the driver connects to. And we have the config server, which I'm going to talk a little about more later, but this is kind of the anchor point. Kind of, you can think of it as the boot sector where this knows where data is located. So everybody syncs from the config server to know where data should be routed and what data they own. The config server durably persists where the data is located, is itself a replica set, so it uses replication for durability and high availability, and does not contain any user data. It's only metadata. It says where things are located. Basically, these 3 partitions that I described. The routers, they cache where data is located by reading it from the config server, and we essentially put it in an STL map, which the ranges, and we use that in order to quickly find out where data should be located. It keeps everything in memory. There's no persistent storage, and speaks the database server protocol. The shards, they cache the information about what data they own. Also, they read it from the config server, and actually contains the actual data of the collection. Collection, mind you, is our equivalent of a table. To remind, the routing metadata looks something like this. It's basically a bunch of BSON documents which say which have this structure. It's from what is the lower bound of the range, the upper bound of the range, what shard it's located on, and a version field, which I'm going to explain in a little bit. The version field is used to make sure that the cache that every node has is coherent with what's the actual state of the data. In a normal operation, we have the config server with the routing metadata, version 1, version 2, version 3. The router has cached the data from the config server at version 3. Version 3 is basically what's the highest version that it has seen from the whole data. And when a request comes, let's say for the name Richard, the router sends that query to shard 3 along with version 3. It tells it, I'm pretty sure that you're at version 3, so I'm going to send this request. If you're not at version 3, don't accept it. And in this case, the cache of the router and the cache of the config, they match, so the data can be served by shard 3. And similar for if there is a request for Igor, which has to go to shard 2. Shard 2 is at version 2, so we just attach that version, and it just matches, and it all works. So now imagine that for some reason the names between Igor and Rachel, suddenly there's a lot of writes there, so this exceeds the capacity of shard 2. We have an internal process which will find what's the best distribution, what are the best partition points of that data. And let's say that it splits it into 3 sub-ranges, from Igor to John, from John to James. Well, actually, it should be, I made it that John sorts before James. Apparently, I don't know my alphabet. But assume that O is before A in our alphabet. And then from James to Rachel. So those are the 3 ranges now that Igor to Rachel became. Does it have a wrong information? Oh, this should be shard 3. And the yep. Yep, definitely. Yes. This is a typo, yes. Minimum is Rachel, 2 plus infinity. That's what happens when you copy paste. Yes, and the version is still 3. And now we have Igor to John, from John to James, and James to Rachel. Those 3 still reside on shard 2. Their version is still at 2 because they haven't moved, so the data stays in one place. And so requests continue to be, the requests from routers that have cached version 3 still continue to be routed correctly. So now, about this is too big. There's the imbalance. There's one partition here, 3 partition here, 1 partitions here. So now the balancer runs and discovers this imbalance. So it says I have to move something somewhere. So it decides to move Igor to John, that range, to shard 3. It tells the shard, now go and move that range. Give it. The shard 2 is called donor, and shard 3 is called the recipient. Now when the move completes, if you notice here, the shard 2, which hosts Igor from John, got changed to shard 3. And its version got bumped to 4 because we modified that entry. And we also bumped the version of shard 2 to 5 in order to indicate that something changed there also, because it no longer owns something. So if a stale router was, for example, asking for something between Igor and John and it went to shard 2, if we hadn't bumped the version, we would still tell it, oh, there's no documents, but the documents are actually over there. So then the router sends the router still thinks that nothing has changed from underneath of it. It sends version fine for Igor and version 2, but now the shard discovers that version 2 is less than version 5. So it tells it, okay, you have the wrong, your routing information is wrong. The router goes, refreshes, and then now it's at version 5, and all the routing executes properly. So this is just a teaser for some of the distributed systems algorithms we deal with. And that's all I have. Yeah. Any questions? Yep.
You said comparing performance-wise, for example, when you do all these things, the indexing is important there. How you build your indexes. So compared to the, how does it manage MongoDB together, or how does it perform?
Right. So the question is, MongoDB compared to relational databases, does it perform better or it perform worse? So first of all, programming with the MongoDB data model, it would be wrong to take a relational model or relational thinking and to model your data in a relational way, but using documents instead. So MongoDB, for example, we try not to do too much normalization. So we try to put all the data together so that so there doesn't have to be joins. Imagine that John, we had the houses of John, for example, in a separate collection. This would be the relational way to do it, where which house belongs to John. If the data was modeled like this, for example, it could happen that the house for John is on shard 1, but the actual information about John is on shard 3, or I guess on shard 2. So now you have to have 2 operations, 2 network latency, 2 network round trips, and so on. So in this case, MongoDB would perform worse than a relational database. If you model your data like this. But if you model your data so that all the information as John is in one document, that document will move together with John. So you just need to do one read. Does that make sense? It really depends how you model your.
You hints to the database like this, because the index
Yeah. So the question is, can you create indexes and yes. So MongoDB does support indexes. Usually when we say that it's flexible schema and you can put whatever you want in the database, but most applications, they actually do have a schema. So you have a name, you have a house, you have a car model. So let's say you want to find everybody that has a Honda, you can put an index of on the field Honda. So that way you have an index to be able to quickly traverse people who have Honda. In a sharded system, for example, where the shard key is the name, because majority, like 99% of the queries are give me some information for a person. The shard key is very useful because it can quickly narrow down which node this contains a particular data. But if you want to find everybody who has a Honda, you need to do a broadcast to every shard, use their local indexes, and then aggregate the results and bring them back. Secondary index. The question is where secondary index is stored, and yes, they are on each shard. Amsterdam, you guys had something?
Yeah, sorry, I didn't realize you also were already talking on the other side. But yeah, we also had a question, but it can go after this one, maybe.
No, you guys can go ahead.
You guys can go ahead.
Okay, dude. 1 second.
I actually have two questions. So first, do you use any insights on the structure of the particular shard? For example, issuing two queries to the secondaries with the intent of canceling the slowest one. And the second one, do you plan to use erasure coding instead of mirroring for data storage?
Okay, so I'm going to start with the first question so I don't forget what it is. I'm going to repeat it. The question is, do we issue, for the same query, do we issue multiple requests to the same shard with the hope that one might hit a closer node and come back quicker? Does this? Yes. So
yes.
It's well, the reason why I was able to rephrase it like this is because we actually have an ongoing project like this, which I believe it's called hedged reads or something like this, where so the user case scenario is I have let's say I'm a telephone company or something like this, where when somebody's making a call, I need to find like within no more than 100 milliseconds, like where do I route that call. And if a request takes 5 minutes, I can't have the customer is not going to sit on the phone and wait for it to ring for 5 minutes. So what they do is they issue more than one request to. So remember how I told you that every shard has three nodes, a primary and two secondaries. So they issued 3 requests to all 3 of the nodes, and which because it's a read, it can read from a secondary. And whichever one returns first, that's what's given to the customer, and the other 2 are just canceled, or if they come back, they're ignored. So yes, we don't do it currently. We have a project somewhere on the books to do it. The second question is about so basically, is the question around what plans do we have about error recovery on the storage engine level?
No, not about error recovery, but about different storage models like erasure coding. So primary reason for having like triple mirroring is the ability to lose one machine, but remain with all that data readable and with like majority available. There are data encoding schemes that give you this property without using 3 times the amount of disk space.
Okay, so correct me if I'm wrong, but I believe these things only work if your replication happens at this disk block level. Is that correct?
Well, the ones I'm aware of is more about block replication, yes.
Yes,
But
they
there may be others.
Yes, so this kind of encoding schemes, while they're very efficient, they operate on the level of disk blocks, and they compare bytes basically and store, I believe, like differences and stuff like that. The MongoDB replication is one level higher than that. We replicate the whole row of documents. We don't replicate like the binary content or something like this. So on disk, different replicas may look very differently than what they look in between each other. So from that point of view, I believe I'm not sure if this is possible, but also we don't have any plans of doing it if it is possible. At least not that I have heard of.
There's an additional detail that replicas are intended to be usable as independent servers. So you're able to query them. They maintain their own indexes, things like that. And so if we used one of the like erasure coding type techniques, you wouldn't be able to query an individual replica if the primary went down. You would have to like combine it with querying everyone else, which would, based on your load, that would probably be effectively an unavailability event. So it actually wouldn't.
But then you also have arbiter nodes for replica sets.
Cut it in 5 minutes. Okay, so we're gonna do 5 more minutes of questions if there are any, and then here we're gonna go and have a beer, and you guys too. Sounds good? So
Yeah, sure does.
So we have one question here. Do you guys have any more questions on your side, Ray?
I think one, right? Yeah. Yes. Okay. Oh, two. If it's possible, we'll start with one.
One from Amsterdam
and one from Barcelona.
Okay.
So go ahead.
It's a question about the storage engine. In the old storage engine, MMAP, per document there was space allocated, and it was only freed after you removed the document. How does that work in the new storage engine, WiredTiger?
So the question is around space management and how is space managed between the old storage engine and the new storage engine. Just as a little bit of context, before 2 releases ago, we were supporting something called mmap v1, which comes from memory mapped, which is like data structures that are sitting in memory, and we literally just write them to disk, like we do fsync from time to time. This is what the storage engine did, and it was a little bit difficult of maintaining free space because now you have a linked list and you put the free blocks on the linked list, but they're not contiguous sometimes. So it was kind of a mess and caused a lot of fragmentation. So you had to run defragmentation. The new storage engine, WiredTiger, and this is a long discussion, but the storage engine is built based on log-based. It uses log-based data structure, which you only append. You don't actually modify anything on site. So as you modify data, you just append new versions to the end, which become the new data, and then you garbage collect the older ones. So there is, I believe, space management is not so much of a problem. The log-based file system takes care of this. Does that make sense?
Yeah, that makes sense. So then the where you have allocated space, which is not big enough for your new log files, is that still a case, or is that fixed in some way?
This is a little bit beyond my knowledge of the storage engine, so I don't think I can answer this.
Okay, it's fine. It's already great. Thanks.
Cool. And one question from Barcelona.
Yeah. Actually, I had a few, but I'll ask you later. So I'll just pick one of them. You
correct me if I'm wrong, when a query is made from the router to the shard and if it's incorrect, yeah, this specifically this case. So the shard tells the router that you have a wrong version of the whole storage of data, so go back to the config server thing and then come back with your query. So this is kind of a reactive update that you had an update already on the shards and then the router doesn't know what's happening. Are you guys also working something on like a proactive update, because that would make your query times much lesser as compared to what you have right now?
So the question is that the current model where the router submits a request and it starts executing and then it discovers that the version doesn't match, then it has to refresh this. This incurs latency now because there is 2 round trips. So the routers, they're very stateless. You're supposed to be able to throw away a router or spawn a new routers whenever you want. And because of this, the nodes, they don't really know how many they are. They're just clients, so they don't register themselves anywhere because they're very ephemeral. So it is difficult to have a push model where you also tell the routers when we call it migration, when the rebalance happens, and also potentially the time that the time to perform this refresh, the versioning mismatch is discovered very, very early. So basically the shard node hasn't done anything. It hasn't started to do writes or anything like that when it discovers. So typically one such round trip is, let's say it delays it by if you have to fetch a few documents, in this case it's just 2 documents because we incrementally refresh, that's 1 or 2 milliseconds and P95 probably. Plus there is, believe it or not, actually the most time was spent in memory on the router. We have and I can talk about this later, but we have incremental patch algorithm where we have the stud map and we remove the ranges that are affected and we insert the new ones. That thing with the large routing table took more time than the network time, actually. It's so slow. So there is some memory blip, but it happens only on rebalancing events, which are fairly rare, and it's actually not that big.
Right. I mean, my related question was like, what's your rebalancing delay? Like, how much time does it take to migrate between the shards?
Yeah, this I feel are questions which are for like a proper talk on the balancer and which I can do, but there's a lot of context behind it and really related to what happens behind the scenes and so on. Okay, cool. So we're done. Thank you everyone. Thank you Amsterdam for attending. Thank you guys.
Thank you. Great. I guess that's it. Yeah, let's have a drink and chat a little. Thanks again, guys.
They don't see you. They don't see you. So you have to do like this. I know, but if you wave here, they see your back. Yes.